first one. I think if I explain Bacchus cone and it needs to work well, then I can easily explain what we did. They did quite a bit of things, but I just want to mention kind of take a cross section of all they did. So it's basically is the following. So they construct basically five different ways, construct 5 different Asian solutions on S15. And so let's see. The first one is basically you realize S15 as this one, as a as a fiber bundle. So this fiber bundle is, you have this canonical line bundle. You can use that unit circle to do such bundles. So what they did is then eventually they get this is t equal to minus infinity. This is t approach to singular time. So eventually this end, so is if you take the blow up limit, this is round S15. That's their solution for this end. That's one of them. This end is like let's see. This end, like you can see, C7. It's like if you don't take any blow up, I think it's just. Let's say if you take a blow up, so you can see the S1 direction is shrinked because you need a blow down actually. By S1 direction is blow down. Eventually you see CP7 approximated with this Fubini-Studi metric. So this is one. The second one is also collapsed. And a sectional curvature. It goes like the following. So you have 2 families. So this is the Einstein metric. This is another Einstein metric. Not the standard one. This is T approach to T minus. This is wrong. So this is T equal to minus infinity. Basically, you can do such Asian solution. Both, it's like similar to the Takahashi example we said before. You go from an Einstein metric because it's not stable, so it's just go out eventually, like attract also to the round one. So that's the second family. Then the third one. So I should say this is the third one. So from different N-state matrix. So then the fourth one. Here you go from an N-state matrix. This is t equal to minus infinity. Here you go to and so the picture is like the following. So it's a kind of you treat this as a Coulombian. This one have a Coulombian standard Coulombian Kähler matrix. Then you have this fiber bundle because this Coulombian manifold have spatial holonomy. That spatial holonomy determines these S3 bundles. I think better to use is use these RP3 bundles here. So you use this then this have because this have a Coulombian structure. This holonomy have a spatial connection here for this fiber bundle. You use the base matrix times a factor, and I use another the standard matrix, round matrix here times another factor. Use the connection, give you this is called a connection type matrix here. Later give you this type of matrix. So the last one is the following. This is the N-state matrix. This t equal to minus infinity. This is t approach to singular time. In this case, you collapsing S7, and eventually the manifold is converges to round S8. This is Gromov-Hausdorff topology. So it cannot be smooth. So you explore this fibrillation structure. Okay, so what we did is the following. So let me take a color chalk. So it's we have this construction of N-state matrix. By Mackenzie, Wang, and Ziller. I use connection type, just so we are kind of generalize this case and this case. So what we did is for each KE manifold with a positive scalar curvature, you can have this use this canonical line bundles to use construct these S1 bundles. So if you take a few products of this one, and we can construct a torus bundle over space. So basically is some product of those line bundles. Then you take some quotient of that. So what we did is then you can use the connection here and or use the standard matrix here, flat matrix here, and use the cage matrix here by times some factor over it. Use the connections here. to construct a matrix of this following type, if we use this is GI, so this is pi I. I will not use. I will not write down this pullback. So it's you can write down matrix of the following type. Let's see. The connection I use let me change the notation. Theta alpha. Let's say use theta alpha. So let me explain this theta alpha in a minute. Write down the connection first. So the matrix is just use GI. The matrix is like this time, this type. So H alpha beta and tau basically is a matrix here. This is a matrix in the fiber direction provided. Then you times some functions of tau only. This is a function of tau only. So there's no dependence on space available. That's why we get ODE. Now, let me explain something else. Maybe I explain here. So here is the bundle structure. So this TR bundle, you can use in different component of TR minus 1. And then you acting on, embedded in TR. Then if you use this action, you look at this P, the whole P space quotient by PR. This will be a S1 bundle over this product manifold. Then, for this bundle, we write down the curvature for the connection. So it's omega I is a killer class I used here, and then we also assume the following thing. C1 of mi equal to pi of omega I. So we assume this one. These are the kind of coefficient, so determining this connection structure. Then what we get is we get an evolution equation. The rich flow equation. This type of connections is preserved by rich flow, this one preserved. So you get this following equation. And the BIS evolution equation is given by this. So just this, this coupled equation. So maybe I just explained a little bit more. So in terms of compared to Bacchus cone and this work is we just move this. They also consider a general K matter. We just change it from one factor to several factors here. Also, we eventually we moved from S1 bundle to torus bundle. And we proved more for S1 bundle. I will explain in a while. For torus bundle, R bigger than 1, we proved much less. You know, the example, we have fewer examples. Another thing is, if you let this equal to 0, it's kind of your flow is not flow. So this equation basically is all this equal to lambda times this BIs. Then this is corresponding to the instant metric. So it's a kind of mixing of these two. That's what we did for one situation. For this equation, we consider we construct several families of Asian solution. That's one case. Mm-hmm. Let me explain the other case. The other one is we extended this construction. So it's in a similar fashion. Is we replace one quaternion Kähler manifold by several quaternion Kähler manifolds. So let's see. So the thing here is the following. Because of the quaternion Kähler manifold, you have spatial holonomy. So originally, you have these spatial holonomy bundles. For any quaternion Kähler QK manifold, you have this bundle. Then if you quotient this SPN part, so if you quotient this by SPN part, so what you get is you get the following bundles. So you get these bundles. So what we did is we want to use a connection type of matrices on those, take the product of them. Then quotient this by diagonals. Then you can construct you have a product of quaternion manifold. So then on this manifold, you can construct this so-called connection type of matrix. Connection is just comes from induced connection from this principal bundle due to the quaternion metric, cage metric. So then let's see. The metric you can on this part you have this metric induced by B1. Let's say use A1 tau BSO3. The factor here, the number of factor here is the same as factor here. This is m of them. This is this killing by linear form, which give you the metric over there. So this one, because you need a quotient, so this take the quotient, induce the metric on this space, you get that one. In the bottom, you have this metric, let's say, same thing as BI top GI. So this, from these two, use the connection here, you can get a connection type of metric here. So once again, this type of connection type of metric, when you consider it's Einstein metric, the Ricci curvature is calculated before. So you get the Ricci flow equation is the following format. This is for m bigger equal to 3. For more than 3 factor. When m equal to 2, because we said m equal to 2, you only have 2 factors since you need a quotient it. So you only actually have 1 effective variable. So that's the one we use this one as the effective variable. So then the equation for this one is given by this. Okay, so A, B are variables. The others are constant. So let me explain the constant. So mi's dimension, because it's a Coulombic scalar, is 4ni. And the capital lambda is defined by the following. So it's kind of related to the characteristic class, so Ricci first 10 class. So I think that basically explains all the equations. So again, our tau is minus t variable. The issue is you want to say, okay, when do you have Asian solution, or tau equal to, your solution can extend it all the way to tau equal to plus infinity for these two systems. Yeah, this system and this system. So that's kind of basically what we did. It's kind of it's a ODE system. And because we do not, we do not know exactly how many variables we use, so we do not basically have this first integral, or we can just integrate the equation, find the solutions of it. So more or less, the study is kind of the qualitative theory of ODE, to that event. Okay, so I think I explained what we did. So I should say again, so this is the joint work with Mackenzie Wang. Okay, so so we explained the equation. Now let me maybe take put this equation up to go over here to see what we can do. So let's consider the case r equal to 1. I think in that case we can say better thing. So So then we let A equal to H11. Because, before you have H alpha and beta, which is a kind of a matrix, H alpha and beta is a matrix of size RR. So since R equal to 1, you only need to use one functions. So the system of equation becomes the following. So becomes this equation. So natural thing, or often a successful thing you do with ODE is you don't take this original form as our answer. You want to do some manipulation, get a better form of ODE. Then in the better form of ODE, things becomes more transparent. So this is what we did, change of variables. My feeling from working, ODE method is sometimes change functions like change AB to YI is more kind of less dramatic than you change an independent variable. It makes the system sometimes much nicer. So I kind of feel this is more impressive. Okay, so if you let EY equal to sigma Ni Qi squared Yi squared. And let Fi equal to 2Pi Yi minus Qi squared Yi squared. So what do we get is we get the equation becomes the following format. So it's kind of tell you your y, your tau variable becomes u variable because of these change of variables. So when you say u go to infinity, corresponding to tau go to infinity, so it becomes you looking for this. Asian solution becomes you look at this equation and u go to infinity, you get a solution exists all the way u to plus infinity. Then the first equation tell you how do you recover a variable. So then you can go from yu solution to here y tau. From y tau solutions, you get it back to ABI. Then you get the Asian solution. So another thing here is this equation now is not so bad because this is quadratic. So, and also, although the total is like a third order in y, but this factor yi is factored out. So actually, the one thing probably you can guess is from over there. This flow equation, if you let it equal to some let Ricci curvature equal to a multiple of the metric. You get an instant metric. So this one, Fi equal to 0 for all the I. Then it gives you instant metric. So now I can draw a picture. So let's say this is C. This is the only Einstein metric of this format. This is known from the old study. This is origin. Because we are talking about Riemannian matrices, so all these things are positive. So we know we only need to worry about this first part. So all the other part is useless. So it eventually now becomes ODE. Becomes a so-called linearization. If you look at the linearization of this equation at C, you will see it have I think in this case is 1 for m equal to 2. You have one positive eigenvalue, one negative eigenvalue. If m is bigger than 2, I should say it, you get let's say, negative eigenvalue is multiplicity m minus 1. And only one positive eigenvalue. So if you imagine you add more this like a more like this in a three-dimensional picture, you can a little bit imagine that kind of thing. So this eigenvalue, there is a theorem in ODE called Hartman theorem. Basically says if you look at what happens to this linearized picture, as long as this linearized equation do not have zero eigenvalue, up to C0 conjugation, you do not have differential. Then the picture, the phase picture, the nonlinear equation is actually similar to the linear equation. This is a negative eigenvalue. Actually, it's a multiplicity of this one, so it's not like a different negative eigenvalue. It's the same thing. This and also similar thing for the Coulombic killer. This is like a algebraic part. We take some energy to to realize it. That's a kind of technical stuff here, mostly algebraic. So you get the picture is one is like this one stable direction is here. The other goes this way, go out. So this way. And what we also proved is this set, this omega set in between here is a kind of preserved by flow. Means if you start within the flow, it must stay here. So you get one here coming out. So this is all the way go to here. That's only one solution go this way. So this is the solution. Actually, this is like our u go to plus infinity. So this is like a Asian solution. Asian is because go to here. ODE solutions, if you do not run to infinity, it must take infinite time to realize it. So we know both backwards limit means go to time minus infinity, and also we know finite time solution, where the solution goes. That's the only one we know. You can imagine you can have solution goes this way. It's also okay. What we did also is the same, is the following. You can find a kind of Lyapunov function. So basically says any solutions, any initial data you start from here. This is the attraction. You can see the solution will go to this way. So this is a kind of, in some sense, is a stable one. So another thing we can argue is this set, you can find one solution go from here to here. This is like a go backwards infinity to an Einstein metric. But as time go to, time go to some t minus. So this basically says among the two factors, one factor is crushed. So another factor survived. I think that's the kind of solution we get. So you can get Asian solution from here, Asian solution from here. So, and also all these kind of Asian solution of this type. So the thing here, when I want to say you get one parameter family of Asian solution is when m bigger equal to 2, this multiplicity is higher. So you basically you have this kind of different solutions go to here. Because of the multiplicity, you have like a hyperplane. It's kind of, hypersurface. You have solution goes there. Then other solutions like probably go like this way. You get this way. Then solution goes there. It's not necessarily Asian because they can show up this way. So
how do you prove the existence? And you use the theory?
You mean
How do you know it's ancient?
Your Asian is you have a ODE. If you start from here, then the solution stop exists. Must you have YT? If the tau, if tau go to some finite time, let's say A, this guy stop exists at A. Either this this one of it maybe say this way go to infinity or go to the boundary. But you can see the boundary it avoids it. It's a pushing. So yeah. The one thing is ODEs have nice thing is when you closer here, because this point make this guy 0. So basically the speed every unit time you go smaller and a smaller distance. That's why you can say it's Asian. It will not stop anywhere short of it. Yeah, that's the kind of ODE. That's why it's compared to PD, it's not much. Okay. So maybe I say what I can do for this R bigger than 1, say this example. So for torus bundle over there, when R bigger than 1, in this picture, you have many directions, including RM. What we can do is we only can recover this part of picture. It means you have a small neighborhood here, then you have near functions. Or any initial data start from here. It eventually converges to 0. That's the only part we can produce the Asian solution. All this part we cannot say anything.
What is the limit?
What is what limit?
The backward limit.
For this one, it's degenerate to this one, to the bottom. Yeah. But this one, you see, for this one, it gives you the instant metric C. Yeah. Okay, so let me let me say let me say a little bit about this Quaternion Keller case. So basically, let's say where is the equation? We go to here. For m bigger equal to 3, for the top case, in a special situation, we also can say something. So we can say quite a bit about the m equal to 2 case. Let me say what we did. So again, you use this change of variables. Then you let EY. So this is the difference.
So I have one question. The OD depends on the initial value.
Yeah.
So if you have two different set of initial value, and then you get two different set of solutions.
Yeah.
But will they time asymptotically be the same when it goes to minus infinity?
So the time is.
Well, if you have two different set of
Yeah,
initial conditions,
right.
you get two set of solutions.
Yeah, right.
But then as time goes to minus infinity,
Yes.
then will these two solutions isometric, or are they distinct solutions? Are they different?
They're different solutions.
They are different.
Yeah.
They
They're
will
just
not be isometric. Or
No, they're just limiting to the same object, but the solution is not isometric.
well, what means that when t goes to minus infinity, will the two become the same? Or?
The limit is the same. Yeah, the limit is the same.
So it's independent of initial value.
Yeah, it depends on here. Here you have difference. If you start from here, it'll give you C. If you start from here, it will give you this one.
Oh, okay.
Yeah, so it's kind of still that picture because it's from ODE point of view. That's a slice in the whole metric space. That is a hyperbolic point.
It is to the limit point.
What?
Depends on how close to the limit point there.
It doesn't matter how close. It's a hyperbolic point. So if you along this line, any close to that, it will go to here. If you on this line, any close to that, it will go to here. So it's because it's a hyperbolic. OD just it's like because of that natural. There is one half here. This is what different from previous equation. There's no one half here. Otherwise, it looks very similar. The one half is because in this case we use this SO3. Eventually, if you quotient this, you get like a kind of S3 RP3. This is not flat. That guy's curvature contributes to this number. The other is flat, so you do not have that number. So then, FIY. Then equation is the following. Okay, so it's if you look at this equation, the structure is very similar to the one over there, except except here. Now in this one, you have a minus one half in it. That's the key thing. So if you draw the picture, so because of that one half, the ellipsoid Fiy equal to, this is the ellipsoid Fiy equal to 0, F1 equal to 0. This is the F2 equal to 0. So you have two ancillary metrics. One is, this is Cassie. Now this is eta, this is origin. What do you get? Now this is a sink. Do the same linearization of that ODE. Try to use Hartman theorem, try to analysis the linear structure. The theorem applies, basically we compute the eigenvalue of the linearized matrix is non-zero. all this real part is non-zero more precisely. Actually, for us, we do not have imaginary part. So this is a sink. This is a hyperbolic point. And here is a source. So once again, since this is a sink, we can get a solution from here to here. Also, a solution, this is a kind of one of the corner. There's another solution from that corner to here. Then you have all these solutions to here. You have one solution go from one instant metric to another instant metric. This set is also preserved by the flow, so you have other metric goes this way. This is hyperbolic, so you have this kind of thing. You have then all go out. So basically, you have a kind of this picture. So once again, we know the following. Maybe I just draw one picture to. I think my time is pretty much up. This is a solution you can know both at infinity, t equal to minus infinity, and at the singular time. This is another solution you know that. This is one more solution you know that. Let's see. This is a hyperbolic. This is the wrong direction. Did I draw something? I think I draw something stupid. Let's say this is a sink. This is a hyperbolic. Sink go this way, so then. So this way. I think this should go away. Something like that. Yeah, something like that. This, that's kind of the picture we have. So when the dimension m bigger than 2, then some of these eigenvalues have multiplicity. Then this is not like a single curve go this way, give you families. So I think I said pretty much what I want to say. Yeah, so I stop here. Yeah.
Do you know anything about the curvature properties of these things?
All these quaternions have positive Ricci curvature. All of them are type 1. Yeah. So in some sense, all of them are non-interesting. You know. Yeah, yes. No, but my non-interesting is kind of not exotic enough. But on the other hand, it's come out of the ODE. So what? No, for Ricci curvature, it's all positive. These metrics all have positive Ricci curvature in this Asian solution.
So you say it's a type 1 Asian?
Yes, type 1.
What's the backward?
Yes.
So type 1
Backwards.
Backward limit should be soliton?
Backward is soliton or is basically instant metric. Go back to your instant metric, or depends on, or it crosses this flat. Depends on whether you blow up or you take only Gromov limit. Oh, no, Gromov-Hausdorff limit, sorry. Just whether you blow up or not. It's basically, it's put this way. This AI tau, either it behaves like a constant, let's say go to infinity, or also BI tau, or behaves linearly. Just basically, so if you have put it this way, either this kind of combination, if you have like a 1 tau, then basically you, if you needed to rescale it, then this factor survives, this factor killed, so the metric will give you this like a low dimensional stuff because all these fiber direction get killed. So you can actually get an asymptotic behavior of these functions. So that's kind of something you can play with OD to twist out.
Now then, let's take the again. So this is the 4
Okay, thanks.